Welcome, everyone. We're very excited to see the audience joining for our Distinguished Ethnobiologist talk with Deborah Pearsall today. She's our 2020 award winner of the DEB Award, our highest lifetime achievement award, and so glad that she can join us. A few housekeeping things for anyone who is in the audience. We are going to leave questions until the very end. If you aren't familiar with the discussion in Q&A yet, it's going to be on the right-hand side of your screen. You can use the discussion or the Q&A button in order to ask those questions. But again, we'll be waiting until the end. Feel free to also use the raise hand function, and we will answer your questions in the order that they are received. Oh, and Gail Wagner's already putting in her congratulations, which is excellent. Sarah as well. Yeah, lots and lots of thumbs up. So we'll get started in just 1 minute. I'm going to pin a quick, and Leslie Main Johnson as well. I'm going to pin a quick image, and then we'll get started. I'm going to share just a few words about Debbie, and then we'll get started with her talk. So this is a really nice image that Debbie shared with us. So because we couldn't all be together in person, we really wanted to honor Deborah Pearsall's amazing achievements in the field of ethnobiology, and we thought that a piece of pottery from where we were originally supposed to have our conference in southern Utah would be very fitting. And so luckily, this piece arrived a few days before the conference, so now Deborah gets to enjoy it. But just to start out today, I wanted to share a few words of some of the achievements of Dr. Deborah Pearsall. So Deborah, as many of you are aware, is nothing short of a giant in the fields of ethnobiology and paleoethnobotany. Dr. Pearsall received her bachelor's in anthropology from the University of Michigan, and then her master's and PhD from the University of Illinois, Champaign-Urbana, both in anthropology. She then went on to a very long career at the University of Missouri, where she continues to be a professor emerita in the Anthropology Department. Dr. Pearsall has written a lot of the books in the fields where she is an expert. Deborah wrote Paleoethnobotany, a handbook of the procedures, and was one of the co-editors for Ethnobiology. She has also penned a number of other distinguished texts in the field, including Plants and People in Ancient Ecuador, Case Studies in Paleoethnobotany, and the Origins of Agriculture in the Neotropics. All along, Deborah Pearsall has shared her expertise through service on a number of boards and committees, including the Society of Ethnobiology. Debbie has served as both the president and president-elect of the Society. We're not the first to honor Debbie's longstanding achievements. In 2002, she was honored with the Fryxell Award for Interdisciplinary Research from the Society of American Archaeology. Deborah also maintains the online Phytolith database with data collected from the Phytoliths of the Flora of Ecuador Project, which ran from 1997 to 2008, which is an amazing resource for anyone that's looked at it or used it. Please join us in congratulating Dr. Deborah Pearsall. It's a little bit weird not to be able to hear the astounding claps right now, but I will now turn it over to Debbie. And we will start her presentation.
Well, let me just say good evening, everyone, and let me begin by saying thank you for this very great honor of being named the 2020 Distinguished Ethnobiologist. It really does mean a lot to me. The Society of Ethnobiology was such an important part of my scholarly life ever since I attended my first meeting which I think was in the spring of 1979, B. Miles Gilbert, a zooarchaeologist who was also at the University of Missouri, was in fact the person that told me about the new society at that time. And we drove together to the meeting. And one of the things I really valued about the society over the years was its breadth and its diversity. And I remember that I used to make a point when I attended the meetings of going to papers that were not about paleoethnobotany, because I never failed to learn something that made me a better teacher and a better researcher and a better ethnobiologist. I also greatly appreciate the help given me by the board of directors, especially Liz and Ashley, in making the arrangements for this presentation and for the canceled trip last spring. Maybe we will get out your way at some point, but we were looking forward to that. Anyway, hopefully no technical fumbles today, but they will be my fault if they happen, I'm sure, because I'm coming up on my 8th year of retirement, and so I've been really spared having to adapt to this new world of virtual teaching and presenting. And so this is, in fact, my first attempt. What I'd like to do today is to talk briefly about interpretation in paleoethnobotany. How do we learn about ancient lifeways through studying biological remains recovered from sites or from the landscape? There we go. Okay. What paleoethnobotanists do, basically, is try to draw robust, convincing inferences about past human behaviors and environmental conditions from fragmentary archaeological and paleo-environmental records of those behaviors and conditions. For investigating past plant-people interrelationships, paleoethnobotanists rely commonly on 4 kinds of remains. These are illustrated on this image of maize. Pollen at the top, phytoliths, cob bodies and leaf bodies are both illustrated there. Macro remains, illustrated by the charred corn kernel and the cob fragment. And finally, starch at the bottom of the image. Let me give you a brief introduction to these remains. Pollen grains are likely familiar to all of us. The wind carries pollen that makes us sneeze. Bees may be so loaded with pollen that we can see it. Some pollen grains are designed for wind dispersal, others for adhering to bees or other pollinators. While composed of tough organic compounds, pollen readily decays in conditions found at most archaeological sites, unless protected from abrasion and decomposers, for example, by burial under an earthen mound, a stone slab, an overturned pottery fragment, or a shell. Wind-dispersed pollen falls onto lakes and can be well preserved in lake bottom sediments. Phytoliths are also inorganic, but unlike other paleoethnobotanical remains, are inorganic. They're also microscopic, but they're inorganic. Silica-based phytoliths are the primary focus of research. Phytoliths are usually well preserved in archaeological and environmental settings, although they can be dissolved under conditions of very high pH. While all the pollen produced by a given plant is virtually the same, this is not necessarily true for phytoliths. Distinctively shaped bodies are formed in the cob, leaves, and other tissues of maize, for example. Not all tissues contain silica inclusions. Maize kernels don't, for example. And not all plants deposit silica to the same degree. Phytolith production is under genetic control. Distinctive phytoliths, you see some examples illustrated here, are produced in many plant families. Macro remains, by definition, are plant tissues visible to the naked eye. They include seeds, such as those illustrated here, fruits and nuts, all plant reproductive structures, wood, roots, tubers, and other vegetative materials. Being organic, macro remains are subject to decay under conditions found in most archaeological sites. Charring, such as perhaps deliberate burning as fuel or trash disposal, or accidental burning, like a cooking accident or a house fire, is a common mode of preservation of macro remains in site settings. Macro remains may also be recovered from lake sediments. Starch serves a vital function in living plants as the primary storage mechanism. Energy storage mechanism. Starch designed for long-term energy storage, such as the grains you see here, is the type targeted by humans for food. It is produced in seeds and underground storage organs. Starch is preserved archaeologically in cooking residues, on the surfaces and in the crevices of stone tools and other artifacts, in human dental calculus, and sometimes in protected settings in site soils and environmental settings. So, how do we draw robust, convincing inferences about past plant-people interrelationships from archaeobotanical data and use those insights to investigate ancient lifeways? The key aspects of this process fall into two broad categories: methodological aspects of interpretation and what can be learned when research questions are approached from different scales of analysis. To illustrate these points briefly this evening, I'm going to use examples from 5 issue-oriented case studies that I researched for my book, Case Studies in Paleoethnobotany. I'll be drawing on examples from the case of Neanderthal lifeways and the paleoethnobotany of maize, social relationships at Cahokia as seen through archaeobotany, the individual and his relationship to the natural world, the case of Utsi, the Tyrolean Iceman, and finally, plants and healing. Let's begin by talking about methodological aspects of making convincing interpretations. And there's 4 of these I'm going to briefly talk about: identification, modeling how assemblages are produced, sampling strategies, and qualitative and quantitative analysis. Identification. Well, this is the basic first step, and any sound interpretation is based on well-identified plant remains. The process of identification is matching of unknown remains of whatever kind to known specimens. A charred corn kernel looks very different than a grain of maize starch, for example, but one goes about identifying them in much the same way. It is often the case that the starch, seeds, wood, phytoliths, or pollen produced by closely related plants is similar morphologically. Or morphologically distinctive macro remains or micro remains may exist within a group of closely related plants, but diagnostic features may be difficult to discern without use of advanced techniques such as scanning electron microscopy, which can just be impractical if you're dealing with a large data set. Quality and mode of preservation can also affect identification of archaeobotanical remains. The taxonomic level of identification achievable for archaeobotanical remains, in other words, are remains identified to the species, the genus, the family, or a higher taxonomic level, is a very significant component of interpretation. Archaeobotanical remains do not exist in a vacuum, however, but are recovered from actual sites, tools, lake cores of known temporal and environmental contexts. A genus level or a family level identification may be sufficient to make a strong argument for medicinal plant use or edible plant use or a past environment in a given setting. For example, our understanding of the paleoethnobotany of maize relies in part on genus-level identifications to trace the early spread of maize from its homeland in Mesoamerica into Central and South America. Maize can be identified based on phytoliths and pollen produced by both maize and the related wild plant teosinte outside the range of the wild relative. For example, in Ecuador, in sediments at Lake San Pablo, as studied by Athens and colleagues. This chart, and you don't have to worry about the details of it, the chart shows the Lake San Pablo core, top to bottom, back to about 6,600 years ago. And you can see that Zea pollen and Zea phytoliths occur throughout this core in various quantities. And the occurrence of the Zea pollen and phytoliths is the foundation for the identification at the identification at the genus level. There also are some species level identifications in here. The maize pollen in the top of the core, for example, is distinctively Zea maize. And there are a scattering of maize cob phytoliths that are also at the species level. Otzi, the Tyrolean Iceman, was a 40 to 50-year-old man who lived during the Copper Age, or the final phase of the late Neolithic, in the Central Alps, and died as a result of being shot in the back with an arrow. His body and associated clothing and gear were preserved by glacial ice. Ogle and colleagues were able to characterize his travels and meals in the days before his death by the genera and families of pollen and seeds characteristic of different altitudes, which were found in his gut. Taking the gut samples in order, and the 5 columns you see are the 5 samples, taking the gut samples in order, based on the pollen he inhaled or drank with water, Otzi traveled down from the subalpine zone, south to a valley bottom, and then back up to the high alpine region to the pass where he was killed. He consumed 3 meals during the last day and a half of his life. And notice the column on the right, the plant genera and families that support this interpretation. Let me talk a little bit now about modeling how assemblages are produced and the role this plays in interpretation. Modeling the specific processes and behaviors that produce a given archaeobotanical assemblage is another important aspect of interpretation. Convincing interpretations demonstrate good understanding of the context of recovered archaeobotanical remains and provide support for the inferred pathway or pathways that brought those remains into the record. For example, consider this model, which illustrates how macro remains of foods, the letter F on the diagram, and wood, the letter W, commonly enter the archaeological record of a habitation site. This is the top of the little diagram. Wood and food macro remains are preserved by charring in hearths, both in the courtyard and in the dwelling in this diagram, and then may be redeposited in garbage midden or on the house floor. The background seed rain and most other debris of utilized plants simply decays away. In cases of exceptional preservation, such as desiccation or waterlogging, much more plant material is likely to be preserved, and it can be challenging to distinguish between natural and anthropogenic processes of deposition. At the Iceman site, for example, preservation of organic materials was exceptional due to waterlogging and preservation in glacier ice. By focusing on materials in direct association with Ötzi's body and gear, Heiss and Oleg were able to remove much of the background noise of the well-preserved seed rain and other natural materials. Bast fiber from the lime tree, for instance, was used as binding for much of Ötzi's gear. Mapping the abundance of lime bast fragments at the site indicated post-depositional movement of his remains. This is a schematic of the Iceman site showing the location of the remains in the center, and then notice the height of the histograms on the lower left, the bast fiber concentrations. These high concentrations of bast fragments in the lower left quadrant of Sector A were in association with a backpack, a bow, and arrow. And this was a slightly elevated rocky area, whereas Ötzi's remains were found in an adjoining depression with much lower concentrations of bast fiber. This pattern of bast distribution indicates movement of the body via cyclical thawing and freezing from its initial position with the objects, the equipment, to the depression. Ötzi's clothing and body picked up some of the bast fiber fragments from his gear. Now, sometimes the inference that a plant recovered archaeologically was likely used as medicine rests solely on the fact that it has medicinal properties, or is considered to have those properties in folk medicine. Such interpretations can be strengthened by eliminating other potential pathways of deposition into the archaeological record for the plants in question. This approach was used in part to argue for medicinal plant use during the Upper Paleolithic by inhabitants of Kotiaskilde Cave in the Republic of Georgia. Pollen of 5 species of medicinal plants was recovered from ancient cave deposits. You see the diagram on the left, the 5 taxa. All 5 of these, however, grew naturally in the area around the cave. By comparing the abundance of modern pollen of the 5 species outside the cave to the abundance of modern pollen of those species inside the cave, researchers demonstrated that the pollen was rarely deposited inside the cave by natural means. The abundances in the ancient deposits therefore indicated human action had introduced those plants to the cave. You'll notice on the table the difference in abundances of pollen outside and inside the cave, helping make the case that this was a medicinal plant brought into the cave and not naturally blown. Let's move on now and talk a bit about sampling. Field sampling is a key element of paleoethnobotanical research. In terms of macro remains, recovering all size classes of remains by flotation or fine sieving is crucial for investigating past plant-people interrelationships that result in deposition and preservation of such tissues. Equally important is designing a sampling strategy for macro remains and microfossils that leads to the recovery of diverse kinds of archaeobotanical data in adequate numbers and well-distributed spatially and temporally that will be needed to address our research questions. Employing a blanket sampling strategy for all archaeobotanical remains is often a good first step. There are also numerous situations in which sampling in small, precisely located areas is essential. Careful attention to sampling is another key component of robust, compelling interpretations of archaeobotanical data. One of the major debates in human evolution is the nature of Neanderthal lifeways and how they differed from those of early modern human populations who overlapped with and eventually replaced Neanderthals and other archaic humans. A key aspect of this debate is the extent to which Neanderthal behavior resembled that of modern humans. Rose and Henry and colleagues investigated this in terms of spatial organization within Tor Farak rock shelter in Jordan. The distribution of phytoliths from monocotyledons, that's A, date palms, B, and dicotyledons, C, across 24 excavation units making up floor 2 of this cave, provided evidence for organization of living space along the lines of modern hunter-gatherers. Grasses were spread on the floor near the back wall and between the hearths, indicating prepared sleeping areas. Phytoliths from grass seeds and palm were concentrated near a central hearth, suggesting a food preparation area. High concentrations of dicot phytoliths beyond the drip line of the shelter suggested construction of a brush windbreak. Many examples could be given of the centrality of food in social relationships. Feasting as a display of social status, differential access to foods by different members of a society, control of the food supply as a way to exercise power, the different contributions of men and women to family meals. We can understand much about social relationships from investigating foodways, but well-contextualized samples are essential. Insights into social relationships in the Cahokia chiefdom are provided by robust macro-remain data relevant to the emergence of elites and relationships among elites and non-elites at the scale of the community, the site, the sub-community, and the household. Fritz and Lopenote, for example, compared abundance of macro remains of maize and native crops from feasting and domestic contexts. Now notice the similarity in the relative abundance of starchy seeds, that's the light gray area on the top of those circles, and these are the maygrass, quinipod, and knotweed. Notice the similarity in the assemblages between the domestic context, A, and the ceremonial context, B. But the distinctive difference in representation of maize macro remains, and that's the black segment of the circle. There was no indication that maize held special social or ceremonial significance, unless it was prepared in a way that left little trace as macro remains. Fritz and Lopenote concluded that dishes prepared and served at communal gatherings called for maygrass, quinipod, and knotweed, traditional staples with long histories of use in the eastern woodlands, with maize being a less essential ingredient. Qualitative and quantitative approaches. Now, there are tried and true approaches for interpreting archaeobotanical data that have led paleoethnobotanists to strong inferences about past plant-people interrelationships. These approaches fall into two broad types: qualitative, in other words, what we learn from determining that a given plant was present at a site or in a context, and quantitative, what is learned from the abundance of the remains that we recover. The point I'd like to make here is that any of these approaches, documenting the occurrence of plants, raw data tabulation, ubiquity, ratios, diversity, multivariate approaches, any and all of these can work well depending on the research question being asked, the strength of the data, and the experience or preference of the analyst. Flotation recovered charred seeds and other potential vegetable foods were among the remains recovered from Neanderthal levels, Mousterian levels, at Kibara Cave in Israel by Lev and colleagues. And these provided a broad potential menu of plant foods in Neanderthal diet. This is an impressive list of plants. And you see basically here a list of all the seeds and fruit fragments identified at Kibara Cave. And these include resources available in spring, early summer, and fall, and include taxa with edible underground storage organs and potential medicinal uses. While it remains very challenging to determine the relative contribution of plant foods in the Neanderthal diet, a diversity of plant foods were clearly on the menu. The first direct evidence for consumption of plant foods by Neanderthals is also based on tabulation of remains. In this case, starch and phytoliths from dental calculus of 3 teeth from an individual from Shanidar Cave in Iraq. These 93 microfossils that you see here, identified by Henry and colleagues, established for the first time that Neanderthals did not live by meat alone. There are many examples in the case studies I reviewed of use of ratios or proportions in making compelling interpretations. This example from Kaman Kapuyuk site in Turkey stands out for me because of the extra challenge of documenting medicinal plant use in a situation of ordinary preservation of macroremains, in other words, by charring. This table shows the macroremain samples from Ottoman contexts containing henbane seeds. Notice in the middle of the table the distinctively high proportion of henbane seeds in H37 hearth sample, which is boxed here for you. Now, henbane is a common weedy plant that produces abundant seeds. So finding seed concentrations in a compelling context was essential for Fenwick and colleagues to make a case for its medicinal use. And in this case, not only is there a markedly high proportion, but H37, the hearth, was a ventilated earth oven, a structure which would have facilitated production of medicinal fumes. The second aspect of interpretation in paleoethnobotany that I'd like to briefly discuss concerns insights that can be gained into past plant-people interrelationships when research questions are approached at different scales of analysis. Each of the case studies I reviewed provided compelling examples of insights gained from integrating individual, group, and landscape scale paleoethnobotanical data. I'll use the maize case study to illustrate. Individual scale paleoethnobotanical data are an essential component of our understanding of the paleoethnobotany of maize. For example, phytoliths and starch recovered from individual stone tool surfaces provide some of the earliest evidence for the use of maize and other crops in the New World. For example, tools from the Balsas River Valley in Mexico, studied by Piperno and colleagues. Tools from Highland Ecuador, studied by Pajan Jimenez. And my own research with colleagues on the coast of Ecuador at Real Alto and other sites. Starch preserved in cooking pot residues provides insights into how maize was prepared and how it was incorporated with other foods into meals. For example, there's a study from pottery residues from coastal Ecuador by Zorillo and colleagues. Finally, starch recovered from individual human dental calculus samples shows the extent to which consumption of maize might vary among individuals. There's a very interesting study from the Caribbean by Mickelberg and Haman Perez. If we look at the group scale, site or group level data are invaluable for providing insights into the relative importance to communities of maize in relationship to other resources, including wild plants and other crops. This is often accomplished by assessing relative abundances of archaeobotanical remains by frequency and ubiquity. And there are a great number of examples of this. I've illustrated one from the American Southwest of a regional look at different phases done by Hard et al. In the Cahokia example I discussed earlier, comparisons at the subcommunity and household level of abundances of maize and native crops of the Eastern Agricultural Complex explored differences in access and use by elites and commoners, and between ceremonial and domestic settings. Landscape scale data of plant-people interrelationships recovered by coring lakes and swamps is essential in documenting the onset and intensification of plant cultivation, including growing maize. Somewhere in that complex graph is the record of maize. Top to bottom is how you read these. Each plant taxon has its own little set of histograms there. Planting crops takes place on the landscape, of course, and by its nature alters vegetation in ways that are visible in sedimentary pollen, phytolith, and charcoal records, like the one you see here in the forested environment of the Amazon. It's very interesting that landscape scale changes with the appearance of crops and an alteration of cover due to cultivation activities and fire on the landscape, that these kinds of changes are in many cases more visible than the actual ancient settlements of the farmers. To sum up then, individual, group, and landscape scale archaeobotanical data have all contributed significantly to our understanding of the paleoethnobotany of maize. Archaeobotanical data lend themselves to multi-scalar approach to interpretation, potentially providing us with multiple lines of evidence concerning many aspects of past plant-people interrelationships. Okay, to conclude here, the development of paleoethnobotany as a discipline mirrors in many ways the development of its parent discipline, archaeology. And without going into a big review of all of this, let's just say that contemporary paleoethnobotany is concerned with searching out any and all aspects of plant-people interrelationships using any and all tools and approaches. We learn about ancient lifeways through studying biological remains, macro remains, pollen, phytoliths, and starch, recovered from sites or from the landscape, and by drawing robust, compelling inferences based on those remains. Strong interpretations are based on rigorous methodology and approaching research questions from different scales of analysis and through multiple lines of evidence. As I continue along my own new and not so new pathways in retirement, my best wishes to everyone. I'm confident that the future continues to be bright for ethnobiology. Thank you very much.